Chapter 2, Section 1 is about the torque. We are going to define the torque. But torque is about an object which is rotating, or torque is the cause which makes an object to rotate, or which makes an object to stop rotation. So then, generally, it's about the rotation of an object. And before starting to define the torque, we should define two terms. One of them is the point mass, the other one is extended mass, or the extended object. So what is the difference between them? So if a sentence or a question defines only the translational motion of an object, so this object is treated as a point mass. If the question or the sentence is about the translational motion of an object, so this object is not important how big or how small, is treated as a point mass. But if a sentence or a question defines the rotational motion of an object, so how big or how small this object is not important, so it is treated as an extended object. So don't forget, point mass, if the sentence or question is defining or asking about the translational motion, this object is assumed to be a point mass. If the sentence or the question is defining the rotational motion of that object, so that object is treated as an extended object. For example, this windmill is in rotational motion. For that reason, we are going to define this windmill as an extended object. But for example, this sentence, it takes 365 days for Earth to revolve around the sun. This revolution is referring about the translational motion. For that reason, so we should take Earth as a point mass in this sentence. Question. This is a sectionary question. In which of the following situations should the object be treated as a point mass? In which should the object be treated as an extended object? So for example, a baseball dropped from the roof of a house. Dropped. This word refers to translational motion. So it's just falling down. For that, it's a point mass. A baseball rolling towards the third base. Rolling refers to the rotational motion, so it is an extended object. A windmill is windmill in the wind. So in the wind, a pinwheel in the wind, so it is rotating. So then it refers to extended object. Earth traveling around the sun. Travel refers to translational motion, so it is the point mass. Okay, now we are ready to define the torque. So before starting to define the torque, now let's get the example given in the book. When the bowling ball strikes the pin, so bowling ball strikes the pins, as shown in the figure, the pins fly backward, spinning in the air, or right or left. So the complicated motion of each pin can be separated into a translational motion, so because it is moving in one direction, also a rotational motion because it is spinning in the air. So then these pins have two types of motion. One of them is translational motion, so treated as a point mass, but also rotating, so must be treated as an extended object. So now what is the cause of this rotation? Now we will understand this. For example, this example is given in the book. When the cat pushes at the outer edge of the door with a force that is perpendicular to the door opens. So it's rotating about a point. So axis of rotation is the hinge here. The door rotates around about a line called the axis of rotation that passes through the hinges. So this is the axis of rotation, and the door is rotating about this point. As you see, this door is in rotational motion, so that's why we should take this door as an extended object. So then, what causes this door to rotate? It is applied force acting on the object, but not only the force. Force produces a torque. Torque is something, a physical quantity, which makes an object to rotate or which stops an object from rotation. So then, torque is a quantity that measures ability and force to rotate an object around some axis. Yes, it can rotate an object, it can start an object to rotate, or it can stop an object from rotation. It's also possible. So, but this is the definition in the book given. Torque is a quantity that measures ability of a force to rotate an object around some axis. So, the perpendicular distance from the axis of rotation to the line along the direction of the force is called lever arm. So, this perpendicular distance from axis of rotation to the force is known as the lever arm or moment arm and represented by D. So then torque in this case is equal to force multiplied by lever arm or force multiplied by moment arm. So then we can get the torque, calculate torque by this equation. So where did we meet the force in the life? Everywhere. For example, opening the door on window, riding a bike, you are rotating the pedal of the bike, or walking or running, you can meet everywhere in your life about the torque. Okay, now equation for the torque is this. This is a wrench. A wrench is rotating a screw right there, but this wrench must apply a force to rotate this this pin, so the wrench itself will also rotate. So applied force is F to the wrench. So distance from axis of rotation, because it's rotating the pin right there, putting the screw right there. So then this distance is D. This distance is D. This is not a moment arm, because moment arm is the perpendicular distance to the force. That's why we are going to say it is the only distance. So equation for calculating the torque is this: torque, tau, which is a Latin tau. F times force applied times from application point of the force to the axis of rotation D. You will multiply this 2 multiplied by the angle between the distance and the force. So theta, sine theta. So this is the general equation for calculating the torque. So unit of torque is Newton times meter. The angle theta is the why Newton times Newton meter. So Newton is the unit of force, meter is the unit of distance. So when you multiply them, it's Newton times meter. The angle theta is the angle between the force and distance. So distance, make distance longer. So the angle between these two lines is the theta, not another angle. You are not going to take this angle. In some questions, this angle is given. No, you will get this angle. So the angle between the force and distance. This angle is this theta, so sine theta. The direction of the lever arm is always perpendicular to the direction of the applied force. Lever arm is what? So this is the force. The perpendicular distance from axis of rotation to the force is this. D sine theta is here, the lever arm. So right here, the lever arm or moment arm is d sine theta. Now, as you see, it's not always d sine theta right here. It can change according to the angle right there. So torque is a vector quantity. For the purpose of the textbook, it is defined as a scalar. Yes, for the purpose of the textbook, it is defined as a scalar, but it doesn't mean that torque is a scalar quantity. Torque is a vector quantity. It has direction. So the sign of the torque is positive if the rotation is counterclockwise. So, and the negative if the rotation is clockwise. So now, for example, this is my pen. I am going to rotate this pen. I am going to treat this an extended object. I am going to put here an axis of rotation. So I'm going to push this pen with a force. Is this pen is rotating counterclockwise? Yes. So then torque is positive. But if I push this pen down in this direction, so it's rotating clockwise. In this case, torque produced by my finger is clockwise, so negative. So if it is torque is taken as positive if rotation is counterclockwise, so negative if rotation is clockwise. For example, if a force of 6 Newton is applied to a wheel of radius 1 meter, how much is the torque on the wheel? So this force is F, given as 6 Newton over a radius of 1 meter, because the wheel is rotating about this point, x of rotation, how much torque is produced on the wheel. So torque is equal to F d sine theta. F is 6. Distance from force to the axis of rotation is 1 meter. Multiplied by sine of angle. Angle between the force and the distance is 90. Sine of 90. So it is 1. So it is clockwise or counterclockwise rotation. Let's check it. So fix it from the axis of rotation and push in the direction of the force. So the object is rotating counterclockwise. So it is positive. It is positive. So positive 6 Newton meter is the torque produced by this force. So in problems, when you are solving a problem, you should obey these steps. First, draw the forces. Yes, I draw the force and record it. So F is equal to 6 Newton. Determine the axis of rotation, which is about which point is the object is rotating. This is the axis of rotation right here. O. Determine the distance and record it. Distance from axis of rotation is the force is 1 meter, so distance is 1 meter. And determine the angle and record it. Angle between the distance and the force is 90, so theta is 90 degrees. So and indicate the sign of the torque if it is rotating the counterclockwise, so it is positive. And calculate it, so Ft sine theta is 6 Newton. Those are the steps for calculating the torque produced by on an object by the force. All right, as I said, if the torque is equal to an equation Ft sine theta, so torque value changes according to angle. Sine 90 is maximum, sine 90 is 1, sine 0 is 0. When the angle between distance and the force is 0, as you see here, torque is minimum, which is 0. Torque is 0. Why? Because sine 0 is 0. Angle between the distance and the force is 0. Sine 0 is 0, so torque becomes 0. But here, angle is not 0, but greater than 0, but not much greater than 90. Angle, the torque, some torque is produced, but this is the minimum torque. Why this angle is smallest? In smallest angle, sine theta becomes smallest, so torque is minimum. So the least torque is produced here. Torque is produced here because the force is the same. We don't change the force. We don't change the distance. We only change the angle. So according to angle, if you write the force, if you try to define the torque, we should check which angle is great. Great angle, so this is 90. So if it is 90, the most torque, the maximum torque is produced. If the angle is smallest, the least torque is produced. So most torque, less torque, and least torque, 0 torque. Okay, so now a question. It says, it's the practice problem. A simple pendulum consists of a 3 kilogram point mass hanging at the end of 2 meter long light string that is connected to a pivot point. Calculate the magnitude of the torque due to the force of gravity around this pivot point when the string makes 5 degrees angle with the vertical. So now we should draw the cases. It's a pendulum. It makes an angle of 5 degrees with the vertical. So when you suspend a pendulum, it stays like this. But you are not going to keep it like this. You are going to pull it and make an angle. You are going to let it to make an angle of 5 degrees with the horizontal. So this angle theta is 5 degrees. So then on the pendulum, which force causes the pendulum to rotate? Of course, it is the gravitational force Fg causes the pendulum to rotate. On the pendulum, is there another force? Yes, there is another force, tension force Ft. But tension force produces 0 torque because if a force angle between the distance and the force is 0, as you see, angle between distance and the force is 0 or 180, so their torque is 0. For that reason, Ft has 0 torque. Only force which produces a torque is Fg here. So then, Fg is equal to mg. We can calculate mg. M is 3 kilogram, g is 9.81, so Fg becomes 29.4. Okay, so Distance is the length of the string. It is given 2 meter long. Distance is 2 meter long. Angle between the distance and the force is this angle. It is the same as that one, so 5 degrees. So 5 degrees the angle. Calculate the torque. Ft sine theta is your angle equation. Sorry, Ft sine theta. F is you calculated, which is Fg, 29.4. Distance from force to the axis of rotation is 2 meters. Angle between the distance and the force is 5 degrees. When you multiply them, this is 5.1 Newton meter. It is the torque. If the magnitude of physical quantity asked, result is always written as positive. Don't forget. Now here, if you put the pendulum on the left, torque is positive because rotation is clockwise. When you push it in this direction, it's clockwise. But if you put the pendulum in the side, it is counterclockwise. Now this is negative in fact, so this is positive. However, question is asking magnitude. If it says magnitude, always you are going to calculate the positive number of the result. Even if the result is negative, when it says magnitude, you are going to write this as positive number. So, question number 2. If the torque required to loosen a nut on a wheel of car has a magnitude of, yes, as you see, again, magnitude of the torque is given, what minimum force must be exerted by the mechanic at the end of 30 centimeter range to loosen the nut? Okay, torque is given 40 Newton meter, so length of the range is 30 centimeter, 0.3 meter. Calculate the force, minimum force. So for minimum force, sine 9 theta must be 1, and at 90 degree, if you apply that force to a range or to a distance, so force becomes minimum. So then torque is equal to F times D times, because sine 90 is 1, you are not going to write it. So for D is equal to force is first minimum will be calculated. Distance is 30 centimeters, which is equal to 0.3 meters. So then divide by 0.3. So divide by 0.3. You will calculate the result as F minimum, which is equal to 133.3 Newton. So now, in general, the ability to rotate an object depends on, according to this equation, torque is equal to Ft sine theta, according to 3 quantities. Force, how much force is applied, distance, where the force is applied, theta, at what angle the force is applied. So these 3 things determine the ability to rotate an object, if you are able to rotate something or not. So these 3 things will determine this. So if the farther the force is from the axis of rotation, which means D is greater, the more torque is produced. So it is easier to rotate an object in this case. Okay, sample problem. This question till now is not asked now, but I'm going to explain this. A basketball is being pushed by 2 players during tip-off. One player exerts a downward force of 11 Newton, so it is a basketball. One force is downward, 11, at a distance of 7 centimeters, so that distance is 7 centimeters, which is equal to 0.07 meter. From the axis of rotation, axis of rotation is the center of the ball. The second player applies an upward force of 15 Newton at perpendicular distance of 40 centimeters from the axis of rotation. So this is the 14 centimeter from axis of rotation, 0.14 meter. Find the net torque. When it says net torque, you are going to calculate the sum of the torques acting on them. So you will find first torque 1 for the first one, torque 2 for the second one. You will add them arithmetically to find the net torque. If more than one force is acting on an object, find the net torque acting on the object by adding up individual torques. So we will calculate them. F1 is given, D1 is given, F2 is given, D2 is given. Angles are given because 90 degree. So if 90 degrees sine 90 is 1, for that is in, you are not going to write it in the equation. So you are going to write torque is equal to F times D. So the first one is producing a torque clockwise direction. So then it is negative. Force 2 is producing a torque again clockwise direction. If you push the object in that direction, so it's also rotating clockwise, so negative, negative. Both torques are negative, according to this picture. So calculate the torque of each force. Torque 1. Force, this is torque F1, according to this given. This is F2. So F1 is 11, because torque is negative. 11 times 0.07, it becomes negative 0.77 Newton meter. Torque 2. 15 times distance is 0.14, negative 15 times 0.14, it is negative 2.1 Newton meter. So calculating net torque, you are going to add up the torque 1 plus torque 2, you will calculate the net torque. Torque 1 is negative 0.77, torque 2 is negative 2.1, so sum of them is equal to negative 8.7 Newton meter. So general students are asking, teacher, how do we know F1 is here, F2 is there? This we don't know. This picture must be given. If not given, we can draw it here, or vice versa. We can draw 11 here, and we can draw the F2 to 15 here. In this case, only sign changes. So right here it is clockwise. When you change their positions, take 11 here and 15 there. So their sign changes. Negative becomes positive, answer becomes positive. Only changes this. The application points of F1 and F2, if it changes, so then the net torque would be positive. Only difference is this. Section review questions. Question number 1. What is the rotation analog of force? Rotational analog of force is torque. Because force translates an object, keeps an object, or lets an object to translate. Torque lets an object to rotate. So that's why they're analog to one another. How does it differ from the force? Torque is generated by applying a force on an existing object. So torque can be zero even if force is not zero. So we can say they are different. On what quantities does it depend? So it depends on three things. Or we can just say that lever arm and the force, or force, distance, and angle. So we can say it like this. Section question number 4. How would the force needed change if you put the handle in the middle of the door? So initially, this is the width of the door. If initially the force is right here, distance is say D. But if you take force in the middle, distance becomes D over 2. If distance decreases, how? For torque produced by this force also decreases. Initially torque is F times T. Finally torque is F D over 2. So that as you see, torque becomes half if you take the force to the middle. So how would the force needed change if you put the handle in the middle of the door? How would the force needed to change? Okay, so if you don't change the force, torque becomes half. But to rotate an object, you need a specific amount of torque. So you need a torque 10, for example, given a number 10. You need to do this 10. How? If distance decreases by 2, you should increase the force by 2 to make again the same number. So to rotate an object, you need a specific number of torque. To provide this, if you decrease the distance, you should increase the force by 2. Calculate the torque for each force acting on the bar in the figure. Assume the axis is the perpendicular to the page and passes through the point O. Now this is the bar. Right here is the axis of rotation. These are the forces acting on the bar. We will find the net torque. So forces are given, no need to draw them, all the forces are given. Angles are given, 23. This angle is given in the book, but remember, we are not going to take this angle, we are going to take the angle between the distance and the force. This angle is needed, so this angle is 90 minus 31, it is 59. This angle is needed for calculating. The other angles are okay. So distance between the angle between the distance and the force is 45. Angle between the distance and the force is 23. Okay, torque 1, positive or negative. So this is the force. Now it is easy to calculate. Fix it from the x rotation. Push in the direction of the force, so it's rotating clockwise. For that, it is negative. Torque 2. So push in the direction of the force rotating counterclockwise, it is positive. This is positive. This is zero torque because the force is acting on axis of rotation. So if a force acts on axis of rotation or its extension passes from the axis of rotation, its torque is zero because there is no distance. There is no momentum, there is no lever arm. So torque 3 is equal to 0. Just you are going to calculate torque 1 and torque 2. Torque 1, negative, yes, negative. What is the force? 10 Newton, 10. What is the distance from force to the axis of rotation? 4 centimeters, 4 centimeters. What is the angle between the distance and the force? Which is 23, 23. So this answer is negative 15.6 Newton meter. Torque 2. Force multiplied by distance. Force is, it's positive. First you put positive sign times distance. Distance is half of that. 4, this is 2. So 25 times 2. Angle between the distance and the force is 59. Sine 59. So answer is 42.89 meters. Torque 3 is equal to 0. When you add them all, you will find the net torque. Negative 15.6 plus 42.8 plus 0, it is 27.3. As you see, answer is positive. If answer is positive, this bar is rotating in counterclockwise direction. So this is the last question of section 1. How does the length of the pedal arm on a Pinafore bicycle affect the amount of torque applied to the front wheel? So this is Pinafore bicycle. It's the pedal of Pinafore bicycle. If you make this pedal longer, in this case torque increases because you apply a force F. If the distance increases, so then according to the equation F times T, torque also increases. So this is the end of first section.